Hi, everyone, and welcome to the Armstrong Fluid Technology webinar series. We appreciate your time today. My name is Armin Danji, and I'm your moderator for today's webinar session. Armstrong Fluid Technology is a global leader in providing the built environment with fluid flow, energy transfer, demand-based automation, and fire safety solutions. In addition, Armstrong 360 Service and Support provides complete solution support for engineers, contractors, owners, and operators. Working in collaboration with Armstrong's partner network, Armstrong provides cost-effective support resources to help you get the best possible performance from your HVAC system at every stage in the life cycle of your building. The title of our webinar today is Psychrometrics and the Properties of Air. This is the first part of a two-part series. We have an amazing lineup of presenters and panel today. Joining us today is Tony Mormino, HVAC Marketing Director with Insight Partners. Co-presenting with Tony Mormino is Tony First, U.S. Director, Application Engineering. On our panel today, we'll have our knowledgeable team of application engineers from the U.S. RSEC team, Mehek Sandhu, Anish Arul-Sitesh, and John Strzok. Before we begin, Mehek posted the Psychrometrics chart in the chat box for anyone that wants to download it or print it to follow along. You can access the chat box through the control panel. We're doing a little something different today, and we'll allow for questions throughout the session. To ask a question, please type your question in the questions section of your GoToWebinar control panel in the top right-hand corner of your screen. I'd now like to hand it over to the presenters today.
Thanks, Armin. Welcome, everybody. And today we're doing something a little different with our webinar series. Tony Mormino, my good friend, and I are going to present and talk about psychrometrics and the properties of air. Tony and I have gotten to know each other very, very well. Insight Partners is one of our major rep firms. They cover a good portion of the Southeast United States. And over the past several years, Tony and I have gotten to know each other quite a bit. We've done some presentations together, and we've talked about doing this to the Armstrong audience to talk about psychrometrics and the properties of air. And everybody's thinking, well, you guys are a pump company and a hydronics company. Why do you need to know and talk about the properties of air? Well, when you look at the properties of air and psychrometrics, they are the fundamental principles of everything that happens in transferring energy within air handlers, within fan coils, to get that energy to transfer over to the water side system to take it back to the chiller plant or the boiler plant. So psychrometrics is really, really critical to everything that we do because it's what the basis of energy transfer is at the air side. And without the air side, the water side doesn't do anything. So you always have that air to water interface. So with that, I'm going to turn this over to my good friend, Tony Mormino, and let Tony get started.
Okay, great. Thank you, Tony. And thank you, Armin, for the introduction, and Joni and Neil for driving the ship here. So I'm Tony Mormino. I'm the marketing guy for Insight Partners. And thank you, Armstrong, for inviting me to do this presentation. We've given this a few times, and I just think it's super, super important. It definitely goes back to the fundamentals and basics of air conditioning and the science thereof. So we got basically about 5 sections here: properties of air, building the chart. We're going to talk about moving around the chart. Then we're going to look at determining some air properties, and we'll have a quick discussion on relative humidity versus dew point, too often confused psychrometric states. And if you have not printed out the Psych Chart, you might want to print it out. It'd be a nice way to follow along here. So when we typically tell people we're going to give a psychrometric prezo, the first thing we hear is boring, right? That is super boring. It's not very exciting. It's just boring, right? Like I didn't sit there and dream as a kid, I can't wait to do psychrometric presentations one day. But you know, what I have found is in my career, it's super important. Like it's like the most fundamental thing and most important thing. And I was really lucky that when I started out, the company that I worked for spent 3 months training us on psychrometrics. You know, like that's how important it is. And it's truly helped me in my career. I've been in the business for about 25 years, mostly in sales, sometimes in management. but it's really been helpful. It's a valuable tool for getting the system designed right the first time, and also for troubleshooting any issues that inevitably will arise. Whether you're in sales or service, an engineer or contractor, in my opinion, this is super, super important stuff. And please post your questions in the chat. We'd love to hear any questions or insight you might have. So talk about the history a little bit. This is the first psychrometric chart, which was basically developed by Willis Carrier. And what he did is he put all these psychrometric properties we're going to talk about into a graphical form so we could see how they interrelate with each other and what happens when we heat and cool air and stuff like that. So psychrometry is the science of air properties and processes of heating, cooling, dehumidification, and humidification is also the cornerstone to the science of HVAC engineering. And just a little fun fact here, the word psychrometric comes from the Greek word sukron, meaning cold, and metron, meaning means of measurement. You will probably never, ever need to know that, but I just think it's kind of neat. Okay, industries where psychrometrics are used. It's not confined to the world of air conditioning. Psychrometrics are used in the fields of agricultural, aeronautical engineering, food engineering, drying of crops, grains, and pharmaceuticals, dehydration, meteorology, and weather reporting. So psychrometrics is used throughout the world, various different sciences. Okay, so the first section we're going to talk about the properties of air, and for this discussion we're going to just discuss dry bulb, wet bulb, dew point, relative humidity, and humidity, which are the most common 5 properties there. There are some other ones, but we're not going to focus on them in this presentation. So we'll start out with dry bulb, which is the easiest. So dry bulb is the temperature of air measured by a thermometer. Basically, it's if you walk out on your porch and you have a little thermometer or temperature reader out there, that's the dry bulb temperature, right? Today and up here in the mountains was 30 when I got up, and it's probably 40 degrees right now. That's the dry bulb temperature, so that's easy enough. So wet bulb temperature. So I think this graphical representation, this is what's called a sling psychrometer, and I think this does a good job of explaining what wet bulb is. So what you'll see here is you'll see two thermometers here. The one on the bottom, well, they're both the same thermometer, but you notice the one on the bottom has the bulb of the thermometer exposed to the air. The one on the top has this cloth sock on there. And what you do is you wet this sock, right? So evaporation is going to occur from the water on this sock. When it does, it's going to cool this thermometer, right? The more water evaporates off of this sock and goes into the air, it's going to provide evaporative cooling, which is going to cool this thermometer. So what you do is you take this handle and you sling this thing around, and I've never used one before. Tony's been around a little longer than me, and he said you have to sling this around for 2 minutes, and I'm like, holy smokers. I mean, engineers must have some big muscles back then or something, because that would take a lot of work for me to do it. But if you swing this around, this evaporative cooling will cool this thermometer, and then you can tell that's the wet bulb temperature there, okay? And you'll note that, the drier the air, you can imagine the more wicking occurs or the more evaporation occurs off of that sock, which will lower the wet bulb temperature. That's why the wet bulb temperature is always lower than the dry bulb. Tony, did I miss anything there? Is that your psychrometer?
Yeah, that's mine that sits in my desk drawer at home. Yes, I am old. Thank you very much. And I still have it. I bought that one many moons ago, and it still works because it's a couple mercury bulb thermometers, and you unscrew the little cap on the end and fill the reservoir with water, and it gets the sock wet, and you stand wherever you want and sling this thing around for 2 minutes. And then you can slide the inner part back into the outer case, and there's a scale on there, and it tells you exactly what the dew point temperature is based on the wet bulb and the dry bulb readings that you've got. The key to it is not getting in places with high wind. So you kind of have to be in somewhat of a sheltered area if you're trying to read outdoor wet bulb and outdoor dry bulb. And you don't want to wait a long time after you've taken your readings. But it's really simple to use. And the cool part is it doesn't require batteries.
This is my sling psychrometer right here. This is what I use. It's easier.
And I have one like that too, because it's.
I'm just joking. These are great. They come in, back in the day, they're coming real big handy. So we're going to talk about that in a minute. So this slide here, we talked about that. The drier they are, the more the wicking and the more the evaporative cooling, the lower the wet bulb. Okay, so it's an indicator of the, the wet bulb has to do with the moisture in there, the dry bulb does not. Okay, moving on to dew point. So dew point measures when the moisture will drop out of suspension of the air. So a little example, so my office here, I just pulled this up, probably can't see it, but it's 54-degree dew point. So anything I bring in here that has a surface temperature colder than 54 will condense, and that's how dew point works, okay? If I brought a drink in from the refrigerator in there that's 40 degrees, it'll condense in here. My window on my office, I just zapped it with the thermometer, it's 60 degrees, so there'll be no condensation on the window. So that's how dew point works.
Do you want to cover why that's important, why dew point's an important measurement for us?
Sure, Tony, you want to take that real quick?
Sure. So what happens is we have to understand dew point, because if we don't understand dew point, then how do we know if our cooling coil is cold enough to do its job? So when we look at cooling coils, and we'll talk about chilled water cooling coils in particular, if I'm sending 45-degree water into my coil, but the dew point temperature of my air is 40 degrees, guess what? I'm not going to take any moisture out of the air. All I'm going to do is sensible cooling. I won't do any latent cooling. If I need that 40-degree dew point, or I need a 35-degree dew point, let's say it's a hospital operating room or some industrial process that needs that really nice dry air, if my chilled water temperature is too warm, I can't do any dehumidification. So I have to know what the dew point is that it's required to get to where I want to be, and that in turn drives my chilled water supply temperature. Because if I don't have the two right, the system won't work.
Great. Thank you, John, and thank you, Tony, for the discussion. Okay, moving on to relative humidity. So relative humidity is a percent of moisture in the air versus how much it can hold. It is relative to the temperature. And to demonstrate what this looks like graphically, we're going to use some cylinders of air here. So let's say you have a cylinder or volume of air at 55 degrees, and you heated that up to 75 degrees. You would imagine the volume would expand, and then we heat it again to 95 degrees to get this container volume of air. So you see those three different volumes of air there at different dry bulb temperatures. So what does 50% relative humidity look like? Well, it looks like this, right? So that's relative humidity. It's the amount of water in the volume of air versus how much it could actually hold. Now, I'll point out that you can see at the first dry bulb condition of 55, right here, and the third dry bulb condition of 95, the relative humidity is the same percentage, but the amount of moisture is vastly different. So we're going to talk a little bit more about that in the end here. Okay. So moving right along.
Tony, quick question, actually. Just based off what you said with the relative humidity, why is it specifically important then? Why wouldn't we use, dew point or possibly other factors? Like, what does it tell us that other factors do not, that would be helpful?
Well, at the end of the day, we use relative humidity because it's an easy to understand number. Okay, for most people, relative humidity is an easy concept to understand. It's relative to the volume of air and the amount of moisture that air can hold. The other thing is, and this is the big driver, if I'm controlling relative humidity in a space, it's much less expensive to put relative humidity transmitters in than it is to put dew point transmitters in. Dew point transmitters are extremely expensive, and so I can replace half a dozen relative humidity transmitters for the cost of a single dew point transmitter. So in that case, it's more cost effective to measure humidity and do the math on the back end and calculate dew point than it is to try to measure dew point.
I agree. Thank you, Anish, for the question, and thank you, Tony. And again, if you're watching and have a question, please put that in the chat. Okay, moving along to humidity, which is, not to be confused with relative humidity. Humidity is the actual amount of moisture in the air as expressed in grains per pound. Okay, so if you took a pound of air and wrung it out like that shirt there, whatever that is, whatever came out of that air volume is the actual amount of moisture in the air. Okay, it's not relative to what it can hold, it's just what is there. So by reference, 100 grains, which would be a pretty good design day in most parts of the country, is equal to about the weight of a quarter, about 0.23 ounces. I believe a volume of 1 pound of air is like 2 point something cubic feet. So if someone wants to Google that and put it in the chat, I just can't remember what that is by memory. So we're not talking about a big volume of air or a lot of water. So, okay, moving on to enthalpy. So enthalpy is the total heat energy in 1 pound of air expressed in BTUs per pound of dry air. So, you know, when we say total heat in air conditioning, we're talking about two things: sensible heat, which is temperature only, and latent heat, which has to do with the moisture content of the air. We talk more about that in part 2 of this presentation. But you know, you could think about it like if you're cooling air down, you have a temperature component, a dry bulb, and then you have to remove moisture from the air by a change of state, which involves some energy. So that's how I think of enthalpy.
Just Tony, just a quick question. What's a practical way to visualize enthalpy? Is there any like example that you can give us? Yeah,
it's a good question. We were talking about this before. If anybody in the chat has an idea about that, let me know. I like to think of a cooling coil. You know, you got air coming in on one side at a temperature and humidity, and then it's leaving at a temperature and a different lower temperature and humidity if everything's working right. You know, that's how I kind of envision enthalpy. But if someone has an answer to that, Tony, you got any insight on that, or?
Run that past me again. I was trying to sort through the questions here real quick.
Oh, no problem. No problem. We were talking about visualizing enthalpy, but I think we talked a little bit about that. So.
Well, and understand that, you know, when we look at temperature and we look at sensible heat's what I can feel. Okay, I can measure it, I can feel it. You know, if I grab something that's hot, I know it's hot. Enthalpy in humidity is the energy you can't feel. And so we know it's there, we can sense it, and we can feel it in the sense that you walk outside and it's hot and muggy, and you feel how oppressive the air is. That's the only way you can really feel enthalpy. Enthalpy is really the mathematical calculation of how much energy there is in that air that we got to get rid of and that we got to deal with.
That's good. I used to live in Florida. You feel a lot of enthalpy in Florida. Let me just tell you that.
Yes, you do.
A lot more than up here in the mountains. Okay, so, all right, we're moving along to our next section. Okay, so we talked about the properties of air. Now we're going to talk about building a psychrometric chart, how this all comes together. You know, at first you look at this and it's extremely busy, and a lot of people don't know where to start, and it's a little bit overwhelming, but we're going to break it down in a real simple form so that even if you're new, it's really easy to understand. There's a link in the chat, I believe, to this chart. You can go ahead and print that out. If you're watching this at a future date on YouTube, I'll put a link in the video description where you can link to it and print it out, because it's really nice to kind of print one out, have it in front of you, and go along with it, especially if you're new. Okay. All right, so let's break this down. So I drew this. We're going to break this down basically into these very, very simple lines and keep it real simple. So this is going to represent the psychrometric chart, and we're going to go here. Okay, so we're going to go through each property and put it on the chart and kind of see how it all comes together. So let's talk about dry bulb first. So if you have your chart, you'll notice on the bottom, that's where the dry bulb temperatures are, and they go, you know, in increasing order from left to right. So it's really cold on the left side, really hot on the right side, and then, so the way this works is, so like right here, if I draw around 90, anything on this line right here, I'm getting pretty good with drawing with this thing, is 90 degrees, right? So anything right here on this line is 110 degrees. So that's kind of how all of the units work. They go in the direction like that. So, okay, so dry bulb. So if you were Willis Carrier back in 1910 and you wanted to plot this stuff, you would probably start with dry bulbs. That's the easiest. Draw those lines, get out your sling psychrometer, spin it around, and get some more points and start putting on this chart, right? So let's say you came out there one day in the morning and it was 50-degree wet bulb and 52 dry. You might put the X there. And then, you know, you came out later in the day and it was 70 wet and I don't know, 68, 78 dry or something like that. And then you got this point here, et cetera, and so forth. So you get that, right? So you just start putting these points together, then you start connecting the X's there and filling this in, and that's how you get your wet bulb lines, right? It's very simple. Just plotting it on the chart. So these go in the direction showed here, down and to the right at an angle there. Okay, so we talked about dry bulb, we talked about wet bulb. Now let's talk a little bit about dew points. So dew point lines run horizontally like this. You'll notice they're not uniform, they are more condensed towards the bottom of the chart, but they run in this direction here. So anything along this line would be a dew point temperature of 30, etc. Okay.
Oh, so Tony, we had a question come in that somebody was asking about equalization with adjacent spaces with possibly different humidity levels. And understand that one of the things that will happen with humidity is humidity will always try to go into equilibrium across a building. It will always try to get to the same value everywhere. And this is the reason we have vapor barriers in buildings. So we have a vapor barrier on the outside wall. You know, you've got your exterior construction, you've got insulation, then you got a vapor barrier between the insulation and the interior surface. We do the same thing. So when you're building a data center, let's say you're going to build a data center in a building, and you want that data center to control to 50% RH all the time. You have to put a vapor barrier behind the wallboard, and it put a vapor barrier that covers the ceiling and the walls. Otherwise, the higher humidity in that space is always going to try to migrate out of that space to the surrounding areas. Humidity is one of those things, it's always going to try to go into equilibrium, just like air pressure is trying to be in equilibrium everywhere in a building.
Yeah, that's a great point. And, there's another factor on the chart we're not going to talk about today, but it's vapor pressure. And vapor pressure is extremely powerful. And you can overcome it by air pressure, but it's extremely hard. So most times there's a vapor barrier. So yeah, that's great. It's great to be knowledgeable on that. We probably hit that in another training, but yeah, very important to pay attention to that. Okay. So relative humidity, was there any more questions on that, Tony?
No, that was it.
Okay, so relative humidity is shown in curves on the chart like this. So I just drew in some arbitrary ones. You can find them on your chart too. So they go like that. Okay, so let's see. So if we plot grains on the chart, put some arbitrary numbers here. You'll notice these are horizontal and they are uniform. And these are the absolute amount of moisture in the air expressed by grains per pound. What's next here? Enthalpy. Okay, enthalpy. So enthalpy in BTUs. You'll notice if you look at your chart, there's some extra lines on the outlying areas of the chart. They're not within like what I've drawn here. And those are the enthalpy lines. We'll look at that a little more here in the next section. We're going to actually draw some lines on here. So that's how enthalpy goes on the chart. Okay. So pretty simple. So when you take all these little components and put them all together, you can see how the chart comes together, right? You've got your dry bulb, drawing your wet bulb lines, drawing your dew point lines, drawing your curves, relative humidity curves. We put the grains on there, and then we got the enthalpy. So you'll see that's how the chart's put together. Pretty simple. What's not shown here, and Tony mentioned this earlier, is vapor pressure, volume of air, and something called SHR, which is sensible heat ratio, which we get into in part 2, which makes the chart even busier. But you can see, for simplicity, we'll just leave it in here at this time. So, okay, so we're going to go through and plot different points on this chart. This is a good time if you have it printed out. You can play along with the chart. Okay, let's enlarge this and go ahead and do some examples. So let's do some dry bulb points first. So let's find 95 on our chart and go ahead and circle that, and I'll help you out here. So 95 dry bulb is right here. Okay, so if you take that and draw a line up, everything on that line represents 95 degrees dry bulb. Okay, next we'll look at 70. So if you want to take your pen or pencil and find 70 right here, go ahead and draw that line up, and there is 70 dry bulb. Now, you'll notice something. If you look at my lines closely, and the lines on the chart, they are offset, right? So I drew the blue lines, I drew perfectly vertical, which I thought the dry bulb lines were for many, many years, until Chris Adams at our company pointed out they're actually not. I thought the charts we were printing were slanted, but the lines actually do not go perfectly up and down. They are a little bit offset, but I drew our line straight just to show you that useless piece of information you'll never need, but thought I'd point it out.
Hey, Tony.
Okay. Yep.
Before we go any further, we got a bunch of questions. So Armin, why don't you fire some of the early questions that we got?
All right, awesome. So Tony, will you cover apparatus dew point?
Not in this session.
Presentation, yeah. Tony, can you hear us?
Yep.
Yeah,
I don't think
we will talk about apparatus dew point much later. That doesn't come in this session. This is really Psychrometrics 101 at this point.
Okay, great. Let's move on to the next one. Is there a smartphone app for measuring wet bulb?
I know there's apps that will calculate the psychrometric properties, but I don't know that there's one that measures wet bulb. Does anyone know? Maybe there's some attachment you can get to an iPhone or a Bluetooth device that connects. I don't know.
There are a couple of different devices out there that you can get as attachments that are basically they're Bluetooth that you can link to your phone. And there are, at last time I looked, there's probably half a dozen Psych Chart programs available through the different app stores. I have a couple of them on my phone from a couple of different manufacturers. They're rather useful because I've gotten to the point where I don't carry a paper Psych Chart with me anymore, and it's easier to do it on my phone.
Mm-hmm.
Yeah, good question.
All right, next one. Which is higher, dew point or wet bulb, and why is there a difference?
Which is higher? So they're kind of in the same plane, I guess, on the chart. I'm wondering if you have a slide that would better answer this. So the dew point of 70 is here, right? And the wet bulb of 70 is there. So they're really the same.
Yeah, they're basically the same value. Yeah, they're basically the same value because they're a horizontal line.
Okay. All right, next one. You ready for the next one, Tony?
Sure.
All right. In thermodynamics, Q is heat energy, yes? Does H measure the Q in air?
Yes, H is enthalpy, and that is the total energy in air.
Okay, perfect. All right. I think this is just a comment. It's important to mention that standard psychrometric charts are for air at sea level. There are special charts for high altitude. So I don't know if you guys want to comment on that.
Yes, very much so. So there are different charts out there. Most charts that you have available are based on sea level. As you move up into high altitude conditions, there are high altitude charts out there. There are also another version of a psychrometric chart called a stoichiometric chart, which looks very, very similar, but it is a high temperature version designed for doing flue gas analysis. So we apply these same principles to flue gases because that helps us understand why condensing boilers do their thing, is understanding the stoichiometric properties of air in flue gas.
Yeah, good question.
All right, next one. When the wet bulb temperature equals dry bulb temperature, what do we infer from that situation? Or will that ever happen?
In that situation, we're at saturation, which means that we are at 100% relative humidity.
Yeah, so that's a good question. That would be something like, I don't know, like the other morning it was 60 degrees and 60 degree wet and dry. That's foggy outside.
Yeah.
So 100%
You basically have fog.
Gotcha.
Good question.
All right. All right, next one. I'll just ask a couple more before I let you return to your presentation. So
Okay.
are there charts that are extended to very warm temperatures? If I have a stack at, say, 220 Fahrenheit, how do we find the air properties?
That's what I was referring to. That in a flue gas stack, if it's flue gases, you can use a stoichiometric chart. There are high temp psychrometric charts. So if that stack is just air, if it's exhaust air, say out of a building or something like that, or high temperature air for drying processes, there are high temperature psych charts that extend beyond the standard 130 degrees that a conventional psych chart runs out to.
Okay. All right, the next two questions, I'll just ask them together and then you can proceed with your presentation. Can you please show us the dew point again on the chart and how many grains in the pound?
So, you know, I have circled here 70 degree dew point right here. And I'll state too, not all charts have the same information in the same place. So you might find the dew point and grains on somebody else's chart different than what you find on our chart. So anyway, so that's 70 there. You can see it looks like the equivalent grains is a little over 110, which is right here. So dew point in humidity ratio, otherwise known as grains in short term. I think that answers the question. Any other questions?
Nope.
All right,
That's
we
it
have
for the moment.
we have a few more. Yeah, let's
gotcha.
continue.
You want to do some more? You want me to go ahead and then we'll do some more in a minute?
Yeah, let's just continue a couple of slides and then we'll stop you again.
And hey, thank you all for the questions. It makes this a lot more enjoyable for us. So thank you all so much for the questions. Okay, so we were plotting the dry bulb. Now let's plot a few wet bulb temperatures. Let's go ahead and plot 70 degrees, which is right here. I already had it circled. So what you do is you find the 70 and you find the line that's, you know, corresponds to that, and you just draw a line down. So that would be 70 degree wet bulb. We'll do 55 wet bulb, which is right here. So if you want to find that on your chart, and it looks like the 55 degree line is right there. So we go ahead and draw that. So we've drawn the wet bulb. Super, super exciting stuff. Okay, dew point, 60 degrees. So we're gonna find the dew point right here of 60 degrees, and you find the adjacent horizontal line, and bing, there you go, 60 degree dew point. Okay, now you know how to plot dry, wet, and dew point. I went a little ahead. So let's look at relative humidity. So if you want to look at the relative humidity curves, we're going to look at 50% RH, which is right here. Remember, these are curves, so you can do your best to kind of draw that in if you like. 20% RH is right here. We'll go ahead and circle that, draw that in, and now you have drawn relative humidity curves. Okay, moving right along here. So enthalpy is a little different. As we noted earlier, enthalpy is here, and there's also enthalpy here, right? So you see these, let me switch over to the highlighter because this is a little hard to explain. So if you see these lines here, that's your enthalpy lines, okay? And over here on this side, they run like this. Hope you guys can see that okay. So you know, something like that. Okay, so the way you would find, let's do 20 BTUs for enthalpy. Let's find out where that is and plot that. So the way you do that, I'm gonna put my pen tool, so you find 20 up here, and you find 20 down here, and you basically take a straight edge and you connect these two and you just draw a line through like this. Oops, got to put this in. There you go. Okay, so something like that. Okay, pretty simple. 40 enthalpy in BTUs is right here and right here. and you just take your straight edge and draw your line. Okay, so that is what enthalpy looks like. All right, so we'll go back now. We'll go back to the chart. So we if there's any questions on that, by the way, please put them in the chat. So we looked at the properties of air. We talked about how the chart's put together. We did some examples of plotting some of the psychrometric properties. Now we're going to move around the chart, and this is called basically psychrometric processes. Okay, so we looked at properties. Now we're going to look at the processes of cooling, heating, humidification, dehumidification, and then points in between those as well. So these are the four primary psychrometric processes, and we're going to see how that shakes out on the chart as far as the directions. Don't worry too much about the details at this point. What we're trying to get is a general feel for if you move from right to left, what's happening with the air, if you move from left to right, etc. Okay, so first we'll start with cooling and heating. Very simple. So let's go to our dry bulb temperatures, which are on the horizontal axis down here in the bottom, and they go, the dry bulb lines go like this. So I plotted two arbitrary temperatures here, right? So what would the process look like if we were cooling air? Which direction will we be moving on the chart, right? Well, it's pretty simple. We'd be going from hot to cold, right? So we're going from this 120 area over to this 60-degree area. So that's what the cooling process looks like. Okay, it's pretty simple. Heating is the opposite of that. So you're going from, a cooler temperature to a warmer temperature. So you'd be heating there. So those are what the cooling and heating processes look like. Okay, next we'll look at humidification and dehumidification, which is just adding moisture and removing moisture, or humidity, if you will. To show that, we're going to look at the dew point temperatures. And I just plotted some arbitrary points here of 40-degree dew point, 70-degree dew point, and 85-degree dew point. So you can imagine if you're moving upwards, you're adding humidity to the air, right? That would be a humidification process if you're moving up, as shown by the dew point lines. And if you're going down, you're removing moisture from the air, you're dehumidifying. Okay, makes sense? Okay. So rarely are we moving in a straight up or down or right to left line. Sometimes when you're just heating, that's just a left to right line. But let's look at cooling and dehumidification to see what that would look like if we were doing that together. So again, cooling looks like this. Dehumidification is in the downward direction, and the combination of the two in this direction would be a cooling and dehumidification process. So anytime you're moving from the general upper right to the lower left of the chart, you're removing heat and removing moisture. Okay, and that should look kind of familiar. That's what the basis for most air conditioning units are. We're moving from a general upper right area to a lower left area. We're removing heat. Okay. Okay, let's look at heating and humidification. So heating the air and adding humidity. Talked about heating earlier is from going from the cooler to the hotter temperatures, of course, and adding humidity to the air moves in an upward direction. So a combination of the two in this direction would be heating and humidifying. Okay. Might do that in like a data center or something like that. Well, maybe not a data center, but anywhere that's really cold and you need a certain relative humidity in the space. Okay. So all together, cooling, heating, humidification, dehumidification. And if you're new and you have a psych chart printed out, you might want to draw some arrows off to the side or something, just as a reminder. Okay.
Hey, Tony.
Yes.
I'm noticing that we're getting a lot of questions about state points and actually plotting processes. And I want to let everybody know that this first part of the webinar was really focused on just being able to understand what all the lines are on a psych chart and which direction the different processes are moving. Like Tony just talked about the heating process and the air conditioning process, which direction we're moving. And when we get into part two, we will spend a whole lot more time talking about the actual state points that you cover going through an air handling unit, going from, you know, outside air and return air through the mixing box, across a cooling coil or across a heating coil, and everything that's going to happen and how to plot that entire process.
Yeah.
Because that's a different process. This is really Psych 101 to get everybody just to familiarize themselves with where everything is at on the chart, where all the lines are, which direction they go. I know we talked about different things about, you know, whether wet bulb and dew point really equal each other, and they don't. Yes, they're on the same horizontal line, but if you look at wet bulb actually moves diagonally, and dew point moves horizontally. So there's a little bit of difference and some things that we got to cover a little bit more in depth, but those will all get covered in part 2, so that everybody can just, we're trying to get everybody on the same playing field as to what their knowledge base is of psychrometrics.
Yeah, and I'm glad you clarified that. I think, yeah, I'm glad you clarified the dew point and the R. Yeah, I wasn't trying to imply they were on the same line there. So thanks for clarifying that for our viewers. And yeah,
Yep.
Think of this presentation as you've never seen a psych chart, you know nothing about this stuff. Like that's kind of where we're at on this one. But,
and
yeah.
we got a request that when we do part 2, they want to have us include discussions about desiccant dehumidification and desiccant humidification. So
Yep,
we
that's a good one.
Put that one in there because that's a different process. It's the same process. It's just looks different.
It looks a lot different than a cooling coil process.
Yes.
That's for sure. So, okay. Yep. Good comments. And we'll talk a little bit about that at the end. We'll show some examples of what's in part 2, which is a lot of what Tony added there. So thank you.
Part of that is, I guess, your
Tony,
wet bulb is going to be higher unless you're at saturation than dew point, right? I think that was the crux of the question before.
Yeah.
Yeah, I'm not sure I understand the question, to be honest with you, but I get what I think what he's asking. Okay.
Okay, let's get started, Tony.
Okay. Thanks for all the questions, by the way. Okay, so where are we at here? Okay. So now we're gonna determine some air properties. Okay, so we talked about the properties of air. We built the chart. We moved around the chart. Now we're gonna talk about determining some of the air properties using the chart. Okay. So if you know 2 of the properties we discussed, you can use the chart to find all the other ones. Okay, you plot the 2 and then you find the other ones. Of course, today, you know, you have these tools like this or apps on your phone. You wouldn't be carrying a psych chart with you, but this gives you an idea of how they relate to each other and how you would find them with the chart. Okay, so let's do this example here. So this readout is a nice fall day here up in Asheville, and it's, I'm going to say 78 dry bulb and 27 relative humidity. So those are our 2 knowns, 78 dry, 27 RH. We'll use those. I'm going to round up and down there. And we're going to determine the wet bulb, enthalpy, and dew point based on those two conditions. Okay. So we know 78 dry bulb. So I'm going to go ahead and get my pen tool and oops, pen tool. So it's about right here. All right. So we'll go ahead and draw that in. 78 wet bulb, 27% RH. Well, here's 30 and here's 20. So you can just, you know, kind of guesstimate where 27 is. It's about right there. Okay. And then we're going to go ahead and draw a dot there, which represents the, you know, the intersection of those 2 points. Now that we know that, we can determine all the other stuff, right? So who wants to determine the wet bulb and put that in the chat real quick? I'm going to plot it here in a second. So if you go up this way, somewhere in this area, and it's 57.5 degrees. So the dew point, okay, so if we want to determine the dew point of this state, we go over here and we find our dew point temperatures, which are right here. So it'll be somewhere in this general area here, which looks like about 41. So it's 41 dew point. And then enthalpy. So what we do to get the enthalpy is we'll line up these enthalpy numbers, right, with our straight edge until one of them goes straight through this point, and that's what the enthalpy is, right? So turns out it's 24.7 or whatever. So, okay, makes sense? Good, got that? Okay. So example 2, we're gonna look at a nice steamy, sweltery day in Florida, 95 degrees dry and 78 wet bulb, and we're gonna determine the dew point grains and relative humidity the same way we just did in the last example. So 95 degree dry bulb, 78 degrees wet bulb. We draw a line straight up here to represent the 95 degree dry bulb. We connect that to the wet bulb of 78 and we draw our dot. Okay, so with those 2 points, now we can determine the other properties of the air, right? So the dew point, we just shoot over here and we see that that is 72 degrees. For the grains, we pull that off the same line. It's kind of hidden under there, but it's about 120 grains. So this would be a very wet, humid design day in Florida, or wherever it would be. The relative humidity curve runs through here like this, and it's 47%. Now, one thing to point out, you would think at 47% relative humidity, it would be a pretty dry, comfortable day. It is not. So that's why RH kind of fails in determining the actual humidity in the air. We're going to look at that in the next section here, but yeah, so. Okay, so I think we're moving on to the final section here. Good on time, Tony? It looks like we are. Okay, yep. So relative humidity versus, okay. So now we're gonna just talk about, we're gonna have a general discussion. This will only take a minute or two about relative humidity versus dew point, okay? When to use which, why it's important to use dew point versus RH, and why it doesn't matter sometimes, okay? So, all right, so just to recap, relative humidity, the value is relative to the dry bulb temperature. I think we've talked about that a few times. The dew point temperature increases in value as the moisture in the air increases, okay? We go back to our example. What does 50% RH look like? So if we have our 3 containers, you know, volumes of air expanding with the dry bulb temperature, go ahead and fill these up and label them like we did before. So this is where we were at before, right? 50% relative humidity in each of these containers. And we're going to assign some numbers to these containers because we're going to take them over to the Psych Chart plot. So we're going to take these 3 points and plot them on the psychrometric chart, okay? And there's the 3 points up there for reference. So first we'll pick out the relative humidity line, which is at 50%, which they all share. And then we'll go ahead and plot the 3 dry bulb temperatures of 55, 75, and 95. And we'll go ahead and fill those in like this. Okay, so what we've got here is a graphical representation. So this point here correlates to what's going on here. 2 correlates to 2, 3, 3, okay? Pretty simple. So let's look at, for kicks, let's go ahead and plot the dew point of each of these state points, right? So we know how to do that now. We just go over to the right, draw a line to the right for each of these. I won't spend a lot of time on it, but then we'll write in their dew point temperatures. Turns out it's 37, 55, and 74. So as we pointed out a few times, what do you notice here? So you notice that the relative humidity of 50% is shared with all these points, but the amount of moisture in there is vastly different. Like there's way more air in this 74 dew point air than there is here. So why is that important? Let's say you had a makeup air unit and you were initiating the dehumidification mode on relative humidity. And you said, anytime it's over 55% RH, I want to dehumidify. Well, this state here, you would not be dehumidifying if you follow that set point, and it's an extremely humid day. So that's why that relative humidity is a little bit hard to use in certain situations. It doesn't really tell you the true nature of what's going on with the air. Does it make sense? Like Tony said earlier, what we typically do is we measure relative humidity and temperature, and we just calculate the dew point so we know what the dew point of the air is that way. It's a lot less expensive, it's a lot easier. And that's why we do it. Okay, so this is just another graphical representation of what we just reviewed, and you could see the RH stays the same the dew point increases. So in summary, we talked about the properties of air. We talked about building the chart, talked about psychrometric processes, and then we determined some air properties, and we discussed relative humidity versus dew point. And is that all I need to know? Am I a psychrometric guru now, expert? Tony, is that all we need to know?
Oh, heavens no. There's a whole lot more to it than this. This is just kind of the beginning to get everybody to understand what a psych chart is. You know, I can remember, well, I can't really remember that far back. When I was in thermo and somebody handed me a psych chart, it made my head spin. And even today, I don't deal with it very often. Usually when I'm out trying to help somebody figure out what's not working right on their system. And so being able to use a psych chart effectively is really, really critical in understanding what is going on in the various stages as we go through a air handling unit to condition the air. And that's what you're going to talk about as we go into part 2, is we're going to talk about all these different processes and all the things that happen as we go through an air handling unit and deliver air to the space as we bring air back to the air handling unit. So this graphic kind of represents everything that's going on and every place that we can use a psych chart. You know, we've got the air absorbing room load, we've got the air going back to the air handler, we've got the mixing at the air handler, we've got the heating and cooling processes as the air moves across the coil, we've got the mixing process of what's going on in the mixing plenum, we've got some exhaust air. All of these things impact what we're doing with the psych chart, and the psych chart can tell us how things are supposed to be behaving as we go through an air handler.
Great.
Great. All right. I know that there's a lot of questions coming in. I will take the next 6 to 7 minutes to go through questions. If we do not get to any of the questions, we have your information. We will reach out to you and we'll make sure that answer your questions. All right. So let's try to go through this. So what is the threshold of elevation change in the psychrometric chart?
I'm not sure.
If I remember, and I'm doing this from memory, so please do not shoot me if I get it wrong. I was thinking it's 2,000 square foot. John, do you remember?
Yeah, I think it's 2,000 foot of altitude. I think ASHRAE has those charts available if you want to download them or purchase them.
Okay. All right. Thanks, guys. Why are all the charts not the same? What chart is considered the most accurate in the industry?
The Insight Partners chart by far is the most accurate in the industry. Doesn't everybody know that? No, I'm just kidding. They're all different. They all have the same. I think they're all foundationally the same, right? Like if you plot 2 points and you find the other 3, they're all going to give you the same value. They just look different.
The thing that I found, Tony, is yes, different manufacturers print them differently. I have 3 different ones sitting on my desk at home, and they all look a little bit different, but they all have the exact same information on it. If I plot the same state points, I get the same answers. I do have one at home that is a high temperature version, and it does look a little bit different because the temperature ranges. It doesn't go as low as a conventional psych chart. It starts about midpoint of a conventional psych chart like we've been using today, and goes to a much higher value. And that's for if I'm doing high temperature air systems or industrial process where I've got hot air that I'm dealing with, those things I have to deal with differently. Like I said, there's a stoichiometric chart, which is for flue gases, and it looks drastically different than a psych chart, but it's all the same information. It's just in a much different temperature range. And because the mix of air is different, it doesn't have the same properties, okay, because there's other gases inside there other than just breathable air. So it behaves differently, and it has different moisture properties and all that goes with it.
The biggest difference I've seen is whether it displays grains per pound of dry air or pounds of water per pound of dry air.
That is
Depends on which units you prefer.
Some of them don't have dew point on there. You just use the wet bulb saturated point as dew point. We kind of looked at it a little bit earlier, but yeah.
Okay. All right, let's move on to the next one. What is the difference between humidity and the relative humidity? I know you covered that, but maybe if you could take 10 seconds to just answer that again.
Yeah, so humidity is the actual amount of moisture in the air, right? Like if you took a pound of air, if you were able to take that, I'm trying to find the slide here, and wring it out and weigh the water, that's the amount of humidity in the air. Relative humidity is the amount that's in the air versus what it can hold at that specific point, which is shown by these
the relative humidity. Keep in mind that the relative humidity is relative to the air temperature at that point and the amount of moisture it can hold at that point versus at saturation.
Yep. So I hope that answers that.
I hope so. All right. Okay, next one. Can you remind me what the dot is at 75 degrees Fahrenheit and 50% relative humidity?
That's for drawing your SHR line. And well, it's called an index point. That's what I call it. I don't know if people call it different things. But
yep.
Where you line up your sensible heat ratio on the chart. And we get into that in the part 2. That's a really good question and really important. So we do talk about that. It's a little hard to explain it without actually showing it, but it's the way to draw the sensible heat ratio, which is the ratio in which air absorbs heat in the space, basically.
Yep. And that's critical to sizing and selecting cooling coils.
Very much so. Mm-hmm.
Yep.
Mm-hmm.
Because if you get it wrong, you won't. If you get it wrong, you won't dehumidify.
Gotcha. All right. So 2 more questions before I wrap up. I know that there has been dozens of questions about when is part 2 series. So guys, hold tight, and we will communicate those details out to you shortly. All right. 2 questions, Tony. So how does the sensor measure percent RH?
Boy, you would have to ask me an electronics question.
I was hoping you knew the answer. I don't know. I'm not really sure.
So there's 2 different types of sensors out on the market. There's a capacitive sensor and then there's a resistive sensor. Depending on which one you're using, whether it's a capacitive or resistive, they have a conductive film on them that is moisture sensitive, and it absorbs and gives up its moisture. And as you pass a current or a voltage across that sensor, the change in voltage or the change in resistance, depending on whether it's a capacitive or resistive sensor, has a chart that it compares it to, and it says, okay, at this change in voltage, this is what the resultant relative humidity is. And you can get them in anywhere from 1%, 3%, 5%, 10% accuracy, and it depends on what you're using it for as to what accuracy level. So if I'm trying to control space humidity in my house, 5% accuracy sensor is just fine. If I'm trying to control relative humidity in a chip manufacturing plant or in a hospital OR, I may want a 1% or a 3% accuracy sensor, but understand the price associated with those goes up. The sensor I have in my house to control my humidifier is about $100. If I put a 1% accuracy sensor in, I could be up over $1,000.
Gotcha. All right. I know that we're over. We were supposed to end at 12 o'clock. Just 3 more minutes and we will wrap up. All right. Okay. Last question, Tony. Is wet bulb a useful property in and of itself? Does anyone actually use wet bulb for anything, or is it just a means to find other more useful properties?
Oh, that's an easy one. Wet bulb is a means to an end. Okay, because what I really care about when I look at a cooling coil, I'm really concerned about dew point temperature and moisture removal and coil performance. And wet bulb is just easy to measure.
That's what it's all about, yeah.
You know, I can take my thermometer. I mean, I've got an electronic thermometer I use out in the field all the time when I get out on job sites. And I've got a little sock made up for the two probes, and I can put both probes in the airstream. One's got the little wet sock on it, one's dry, and I can get wet bulb and dry bulb. And then I can take that back plotted on a Psych chart, and I can tell you everything else. And if I look at that from entering and leaving coil conditions, I can tell you what the coil's doing. I can tell you whether or not the coil is working properly. You know, I can use some of this information to help figure out whether I've got bypass problems, whether I've got airflow problems, whether I've got water flow problems, or whether I've got water temperature problems. All these things play in together to give me a true picture of what the air handler is actually doing.
Okay, Tony Mormino, anything to add?
Nope, that's well said. Yep.
Okay,
It's easy
awesome.
to measure. Yeah.
All right, so as promised, we're going to wrap up, guys. Thank you so much. Thank you, Tony First, Tony Mormino, Mehek, Anish, and John. Thank you all for joining. I know that this has been a very informative session. I've been getting comments about how great the session has been. So congrats, Tony Mormino and Tony First, on doing a great job. To learn more about Armstrong's cooling solutions for data centers, please contact our team. As mentioned earlier, today's webinar is part of a two-part series. A lot of you have been asking about the second webinar, so we will communicate those details to you shortly. A recording of this webinar will also be to you via email, and that email will come from Armstrong Communication. A lot of you have been asking about the PDA certificate. That will also be sent to all the attendees, and that email will come from Armstrong Fluid Technology. Thank you again for your time. Please stay safe and in good health. Thanks again. Bye-bye.
Thanks, everybody. Appreciate the time today.
Thank you.
Thank you.
Thanks for having me.
Thanks, everyone.
Thank you.